My name is Guy, and the title of this talk today is Transforming the Database, Critical Innovations for Performance at Scale. I'm head of training at ScyllaDB, and my job here is to lead the training both on-site and off-site. My background is as a software engineer, and I'm based in Israel. And what I would like to talk today about is I'll start with a quick history of hardware and databases, just so we have a context of how we got where we are today. After that, I will talk about NoSQL and specifically about ScyllaDB. Then I will talk about the architecture of Scylla, which is also relevant for other databases such as Apache Cassandra, Bigtable, and others. I'll talk specifically about performance, talking about some optimizations that we used when we designed the database. And if we have enough time, I'll show a benchmark of a petabyte cluster. And then I would definitely like to leave enough time for Q&A. So before we actually get started, I have a quick question. What is your NoSQL status? And let me see if I can, maybe Vered, you can help me do a poll here in Zoom. Do you know how to do that? How do I create a poll? Okay, just to save time, I'll read you the answers, and if you could write on the chat window. So what is your NoSQL status? The first option is I haven't heard about NoSQL before. The second option is I heard about NoSQL, but I've never tried it. And the third option is I've used NoSQL databases before. So let's take a minute just so I have an idea who I'm talking with and what's your background. If you can take a minute and answer in the chat. Again, the first option, the question is, what is your NoSQL status? And the options are, I have never heard about NoSQL. The second option is I heard about NoSQL, but I haven't used it before. And the third option is I've used NoSQL databases. Okay, great. So I see those of you that answered, we have a mixed result. Some heard about it, but never used. And I see quite a few people have used NoSQL databases before. Great, so I'll keep that in mind when I go over the NoSQL part that you already, some of you have some experience. Great, so let me start with a quick history of hardware and databases, just to understand where we are today. So typically, or traditionally, databases were mainframes. Imagine a bank, and in the basement, there's a big computer, mainframe, that holds all the data that the bank needs. That was back in the 70s. And those databases used the relational or CQL model. And Oracle was a leader back then. And that became pretty much a de facto standard. And when I studied software engineering, that's what we learned. We learned about SQL databases. In the 90s, as networks develop, and definitely about 20 years ago when the internet explodes, we have a situation where we have a lot of data, and NoSQL databases are invented. NoSQL databases are distributed, and that means that they run on more than one computer. Typically, they have a more flexible schema, and they offer better performance and higher availability. So that was back in the 2000s, 20 years ago or so. In 2008, we have the beginning of Apache Cassandra, an open source database based on the Bigtable paper written by people at Google and some other people, and some other databases that provide NoSQL results, and they scale, they offer high availability, but eventual consistency. And I'll talk a bit more about what that means in just a bit. All this worked fine. However, there were, in the last 15 years, some changes in the hardware world. And about 7 or 8 years ago, 2014, 2015, databases like ScyllaDB, CockroachDB, Yugabyte, and some others were built, also called new generation NoSQL databases. And they use similar algorithms to Cassandra and others. However, they also utilize modern hardware. And this is what I'm going to speak about in the talk today. So what happened back from the 70s in terms of hardware? So most of you probably heard about Moore's law. It's not really a law, it's more like a rule of thumb that states that every 2 years, the number of transistors doubles. And you can see that here in orange. And we can see that while it might reach a limit, it's still doubling and still standing. However, what's interesting here is we see that about 15 years ago, the performance or basically the performance of a single CPU or a thread pretty much plateaued. So you can see that happened somewhere in 2005, and it increased very slightly. And that happens together with the frequency, which from the 70s was going higher. The frequency back in 2005 or so was plateauing as well. So there was a physical limitation where a lot of heat was being generated and the frequency could not be increased. What's also interesting in this chart is that the number of logical cores increased at around the same time. So we see that at 2005, back in the day, I'm sure some of you still remember those days like myself, computers had a single CPU. We can see that here. But somewhere around 2005, computers start to have multiple cores. And today, a standard laptop has 4 cores, and we have servers that have 64, 128, or even more cores in production, and that's becoming the new normal, so that's going up. So what happened? I mentioned that the per thread performance plateaued, and the core number went from 1 to 256. Together with that, the memory became cheaper, and also the technology improved from 2 gigabytes back in the day. Now it's 2 terabytes easily. The disk also changed, also in terms of space. So we used to talk about 10 gigabyte hard disk space. Today it's easily 10 terabytes. And also very importantly, the technology of hard drives changed from mechanically spinning hard drives to SSDs, which reduces the seek time by an order of magnitude from 10 to 20 milliseconds to 20 microseconds. So that's very important. And we also have a network throughput increase and some other changes. So with that background in mind, let me talk about NoSQL and Scylla. So I won't talk too much about NoSQL, seeing that many of you are already experienced in it, used it, or heard about it. But let me talk about what we see here, which is also called the CAP theorem. And the CAP theorem states that there are 3 attributes we would like to optimize in modern databases or distributed databases. And they are consistency, availability, and partition tolerance. However, there's a trade-off between the 3, and we have to give preference to 2 out of the 3. We can't have it all, right? So what do those mean? So consistency means that for every read that we perform, we will get the latest write. Availability means that our system will always be up and running. And partition tolerance means that even if there's a network failure or some messages don't pass, the system can still serve requests. Okay, and I put here some logos of familiar databases. By the way, the database world is very big. Over 200 databases that I know of that are news. Cassandra being one of the top 10, and DynamoDB also being probably in the top 20. So, for example, MySQL gives availability and consistency a preference over partition tolerance, whereas MongoDB and some others prefer consistency over availability. ScyllaDB, as well as Cassandra and Amazon DynamoDB and many others, they give preference to availability over consistency. And that means that the systems remain highly available, and we have something that's called eventual consistency. Okay, and I'll talk about that in just a bit. Another way to look or to classify NoSQL databases is according to the data model. And here, going from from less complex to more complex, we have key value stores where there's simply a key and a value, document stores, think about storing XML or JSON, wide column stores like ScyllaDB and Cassandra, where you actually have a table with rows and columns that are stored. And the most complex are graph database systems, such as Janus Graph and Neo4j, and their data is stored as edges and nodes. Okay, so a few words about ScyllaDB. ScyllaDB was founded about 8 years ago by two founders. They were the designers of the KVM hypervisor, which is part of the kernel Linux today, if some of you are familiar with that. And it was written as open source software from the get-go in C++. And today, we have a product that provides very high performance. So when comparing to some of our competitors, to other databases, we have ×5 higher throughput. Throughput is the number of queries that we can perform per second. We have up to ×20 lower latency. Latency is how long it takes to perform a query. And just to give you an idea, in Scylla, we have queries that take usually 1 or 2 milliseconds. So that's quite fast. And maybe if we have time, I'll show you some benchmarks. And also not more, but very importantly, we get very high cost savings. So when we compare to other databases, because we can utilize the hardware to its full capacity, we don't need so much hardware, right? So we need less servers, and that translates to less resources and less money. Scylla is API compatible with Apache Cassandra and with DynamoDB. And that means that if you're currently running an application with Apache Cassandra or DynamoDB, you can simply take your application as it is, change the underlying database to Scylla, and get some of those benefits without much effort. We offer 3 different flavors of Scylla. So the first one I mentioned is the open source software. And if you go to our website, ScyllaDB.com, you can go to the GitHub project, download the code, have a look at it, compile it yourself if you have a few hours, play around with it, and maybe even contribute some code. So that's adequate for some people. And then we have our enterprise offering, which is closed source, and that's based on the open source solution. And with the enterprise version, we offer additional features, things that are related to performance optimizations, security, and others. And with that, our customers also get 24/7 support, which is important for large customers. And last but not least, we have our database as a service or cloud offering, where we manage the database for you. So we run Scylla on the cloud, and you don't have to worry about backups, about repairs, about security, about updates. We take care of all of that for you. And you can just focus on your core business of developing applications. Scylla is used by more than 400 companies, some big names that you probably heard about, like Starbucks, Zillow, I don't know, some others, Comcast. And some of the attributes of Scylla, and a lot of what I'm going to say today, also when I talk about the architecture, is going to be relevant to Apache Cassandra and some other databases as well. So Scylla is used as an example here. So the first attribute I mentioned already is high availability. And that means that typically Scylla runs on at least 3 nodes, and it can also run on hundreds of nodes. And that means that we have redundancy and we don't have a single point of failure. So data is replicated across the different nodes. And even if we have a situation where some nodes become unavailable, or there is a network failure, the database can still serve requests. The database is highly scalable, and that means that you can add or remove node as needed without any downtime. So recently it was Black Friday. If you're an e-commerce website, you probably needed more, you needed to serve more requests. So you could simply add more nodes, scaling up your database, and maybe after Black Friday, you could scale it back down. And that's very easy to do, and it's done without any downtime. Performance, I already mentioned, so very high performance. Low maintenance is also quite important. So if you're familiar with Apache Cassandra, things like garbage collection optimization, worrying about JVM, Java Virtual Machine, you don't really have to worry about that in Scylla. It's self and auto tuning, and it does a lot of that for you. And I already mentioned that it's a drop-in replacement for Apache Cassandra as well as for DynamoDB. Okay, there's a lot to cover, and before I go on, I want to tell you about ScyllaDB University. And ScyllaDB University is a free online training resource center. And we have quite a lot of material about NoSQL in general and about ScyllaDB specifically. And you can just create a user, it's free, and take some courses. It's a mix of hands-on labs and videos and slides and text and other quizzes and interesting stuff. So feel free to check that out. And we have, well, if I would have more time, I would show you an actual lab, but you can see that on Scylla University. And this is a lab of just getting started with Scylla. So it runs in your browser, creates a virtual environment. You don't have to install anything. And simply by copying the commands, you understand what each command does, and you can get started with running Scylla cluster and performing some queries. Great. So I've been talking for a while just to make sure that you're still with me. Another question for you. So how many of you have heard about ScyllaDB before? If you can answer that in your chat window. Have you heard about ScyllaDB before? 1 would be yes, 2 would be no. And I'm curious to hear. Maybe some of you are already using ScyllaDB. I don't know. So again, how many of you heard about ScyllaDB before? 1 is yes, I heard about it. 2 is no. So people heard about it. Some people did, some people didn't. And I'm happy to see that people are still alive and answering. Yeah. By the way, also feel free to ask questions in the chat window. I'll try to see it as I talk, and if not, I'll try to answer in the Q&A part after my talk. Okay, so thank you for that. Now I want to talk very briefly about the architecture of ScyllaDB. And again, this is relevant almost one-to-one to Apache Cassandra and to some other databases. So this will give you an idea about what happens under the hood in distributed NoSQL databases. Great. So the most basic unit that we think about is a node. It's quite a common term. And basically, a node in Scylla is a computer or a server running the Scylla software. A node consists of shards, and I'll talk about that in just a bit. And in Scylla, each node contains a part of the database content, right? So I mentioned data is replicated. That means that we hold, or the database holds, multiple copies of each piece of data, and each node is responsible for a part of that data. In Scylla, all nodes are created equal. Okay, we don't have the idea of master-slave nodes or leader-follower, however you want to call it. All the nodes are the same. And that means that even if one or more nodes become unavailable for whatever reason, maybe there's a fire, an earthquake, a network failure, whatever, the system can still serve requests. Okay, that goes together with high availability. The next term is a cluster, also called a node ring, and that is a collection of nodes that work together. In this example that you see here, we have just 5 nodes. A system in production should have at least 3 nodes, and it can go all the way up to hundreds of nodes working in a single cluster, depending on your needs. A system can have more than one cluster, but typically it has one cluster. And an important thing to note here is that all the internode communication is done peer-to-peer. Okay, so the nodes communicate among themselves. And again, that means that we don't have a single point of failure here. Okay, that takes me to an important concept called the partition key. And this is how the database partitions the data. So what does that mean? We have an example row here with ID, name, address, and phone. And here the partition key was defined to be the ID. Now, when an application or me as a user wants to write, say I want to write this row to the database, I'm looking at a database with 3 nodes. And what Scylla would do is it would perform the partition hash function on the partition key, and it would get a value, which is the hash. And according to the hash, it would know which nodes are responsible for this specific data. Okay, and that can be more than one node. So each node is responsible for a set of token ranges. And according to the consistent hash function performed on the partition key, Scylla node knows which nodes are responsible for that given data. I mentioned data replication. So an important concept is replication factor, and that determines the number of nodes where data are replicated. Okay, so this is something that is configurable, and we set it per key space. Okay, and there can be different values, and of course that has an impact also on the availability and also on the resources that we use. So if we have, let's say, a 5-node cluster, and we define the replication factor to be 3, that means that each piece of data or each row will be replicated to 3 different nodes. Okay, so obviously if I set a replication factor of 5, I will have more redundancy, but then I would also need more storage and more resources. So the replication factor is defined per key space, and the replication itself is done automatically. So once you define it as a user, you don't have to worry about it. You don't have to do anything to actually replicate the data. Another important concept is the consistency level, or CL, and that is the number of nodes that must acknowledge a read or a write. So some possible values are 1, quorum, local quorum, and all. And this consistency level is tunable. And that means that it can be set per operation. Okay, so maybe in my application, I have writes that need to be more consistent than the reads, or maybe there are different types of writes. I can set the consistency level as per my use case and as per my application. Let me give you a quick example, maybe to explain how it works. So if I have, going to the previous example, if I have a 5-node cluster and a replication factor of 3, and I try to read a specific row, then if I define the consistency level to be quorum, that means that 2 out of the 3 nodes need to respond to the query for the query to be considered successful. Okay, so that means that if out of my 3 replica nodes, 1 node is down, we can still serve requests. However, if 2 nodes are down, then the query will fail. Okay, and this is something that I can control. One more concept is the data center. So Scylla is built in a way that's aware of the data center topologies. We can have multiple data centers, and this serves 2 main purposes. One is that it would make more sense to serve requests to a user in the US from the US data center and not from Asia. And the second is that this creates extra redundancy and high availability. So if we have 2 data centers and there's a disaster in the Asia data center, the US data center would still be up and running and serving requests. And afterwards, after the Asia data center is up and running again, it would resync to the US data center and be able to serve requests as well. Okay. Maybe another point here that's also important is that for some, I would say, political reasons or compliance reasons, maybe, sometimes data of users needs to be stored only in the same country or in the same geographical location. And with a topology-aware architecture, we can achieve that. So maybe, I don't know, users from the EU, there's a regulation that all their data needs to stay within the EU. So we can quite easily do that. And after talking about architecture, I see a question about shards, and I'm going to explain that right away. So it's a good question because I have a slide on that. Before I get to shards, let me talk about benchmarking. I mentioned performance. So typically it's measured in throughput and also in latency. And here we have some comparisons or benchmarks that we did with comparing ScyllaDB to other databases like DynamoDB or Cassandra. And you can see the results here. I don't really want to get into this, but just one example. If we compare to Cassandra, so we ran the same workload with 4 ScyllaDB nodes working against 40 Cassandra nodes. And the results were that we were 2.5 less expensive, but we offered up to 22 times better latencies. Okay, so it's easy to understand why this would create value to use Scylla instead of Cassandra. And if you're interested, check out our website. There's a lot of benchmarks there. So talking about shards, this is quite an interesting topic. So traditionally in Cassandra, in other NoSQL databases, there is the threading architecture. And by using threads, that means that we have a thread pool. And whenever we have a job coming, a thread is assigned to that job. And the thread needs to get resources, and then it can take care of that job. And what happens there is when we profiled those databases, we saw that there is a lot of CPU time wasted on things like waiting for resources, deadlocks, idle time, and stuff like that. And you can think about that as what we see here on the left-hand side. Okay, so we have here 12 bowls of food and 12 puppies, and all of them want to eat. But we have some bowls that are empty, and some puppies are eating from the same bowl. There's some food on the ground, and it's quite messy. So the puppies are not so happy. And in the database world, this translates to high latency and the lower throughput. Now, the shard per core architecture that we use in Scylla, so you can think about it as what you see here on the right side. So we have 12 bowls of food and 12 puppies, but in this case, each puppy is eating from their own bowl, okay? So it's obviously less messy and the puppies are way happier. In database language, that translates to lower latency and higher throughput. And the way that that works is that Scylla, when it's configured, what it does is it looks at the number of cores and it works on a shard per core level. And that means that it assigns resources to each shard. And that means, well, the CPU itself, memory, also networking, and also a part of the data that that shard is responsible for, okay? And by doing that, we have resources allocated to shards. Each shard is responsible for a range of the tokens and a part of the data. And then we don't have to waste so much time on context switching, on deadlocks, on waiting for hardware resources. And this is the slide that I showed you before. And this is something that's used in distributed databases in general. And I mentioned the way it's done is that, well, what I told you before wasn't completely accurate. I said that the partitioning hash function knows which node is responsible for the data. So actually that's not the case. The partitioning hash function knows which shard in which node is responsible for that data, and it sends the data specifically to that shard, okay? And that brings me to the C-star framework. The C-star framework is an open source framework, also developed by ScyllaDB, and it's powering ScyllaDB, but also some other products like Red Panda, Value Store, and some others. If you're curious, you can have a look at the GitHub project, have a look at the code. And the C-star is basically a mini operating system in the user space. So instead of using the task scheduler and the IO scheduler in the kernel, it takes that to the user space and it optimizes it for using the shard per core architecture. It uses direct IO and self-managed cache. And I won't go into the details, but Scylla is based on the C-star framework. And if you're interested in that, you can have a look at the GitHub project. Finally, I'll talk about workload prioritization. So typically a database has two types of workloads. One is analytics. And with analytics, we typically have, think about business intelligence. We have large work items, it's throughput oriented, and we want to work on large amounts of data, but maybe the performance is not that important to us. We don't need millisecond answers for our queries. On the other hand, you have OLTP, which is online transaction processing. And there you have small work items. It's very latency sensitive. And think about, I don't know, IoT, where you're writing something every second and you just need to record that on your database. So in Scylla, workload prioritization is a feature that allows the user to define how many or how much of the resources are used for each workload. And of course, that depends on your application. And then Scylla would give preference according to the definition of what you prefer. Another way to think about it is OLAP is like a big truck. It's slow, but it deals with a lot of data, while OLTP is like a race car. It goes fast, but it's smaller. And with workload prioritization, we can make conflicting loads work on the same database. Now, seeing that we're almost out of time, there's the Petabyte benchmark. It's interesting, but I won't talk about it just because we lack time. You can see it on our website. Maybe in one word, we achieved, you can see the results here. We achieved P99 latencies. P99 is like the worst case latency of a query. And we achieved 7 million operations per second with a latency of less than 7 milliseconds for writes and about 2 milliseconds for reads. So that's quite impressive. experience Scylla for yourself. So again, you can download the software, play around with it. It's open source. You can check out Scylla University. You have the link here, or just Google Scylla University. And we have a new community forum. I mentioned it's open source, so you can come and say hi, ask for features, share your tips, and just network with your colleagues. That's our new forum. And we have time for questions. Before that, we are holding Scylla Summit. It's going to happen in February. So that's like 2 months from now. And there's going to be a training part, but also a lot of interesting talks. And it's going to be both physical and virtual or online. So you're welcome to join us for that. It's free. And we're also hiring. So if you want to join the company, have a look at our website on careers or shoot me an email. We're always looking for talented people from around the world. Also, if you have any feedback, if you want to get a copy of the slides, you can just write me an email. It's guy@ScyllaDB.com. Great. So thank you for joining. I appreciate your time and hope to see you around soon. Bye for now.
Thank you, Guy. Bye.